As I mentioned last time, L'Hopital's rule stated to only work for 0 over 0, but it can be extended to the form infinity over infinity. And it could be positive infinity or negative infinity. The only reason it's not presented that way is the proof for that requires some tools beyond what we have so far. But we're going to take advantage of that fact in here. So I want to do an example of where we have a ratio of infinities. So for example, say we wanted to evaluate the limit as x goes to infinity of natural log of x over x. So x is easy. We know that as x goes to infinity, x goes to infinity. Natural log of x, we'll be looking at logs quite a bit in the future. So let's just remind ourselves what the behavior of logs are. Let's just think about the sketch here. Remember, it has a vertical asymptote here at 0. It's not defined at 0. It's 0 at 1. So it's, and then it's a lot less steep after 1 than it was before. And if you recall, it was defined, we defined the log, natural log, to be the inverse of e to the x. So we really know that behavior because we know if you flip that over the line y equal x, that should be the picture of natural log because it's defined to be the inverse. Now, a common misconception is to plug natural log into a calculator or Desmos or something and think that, well, that's growing pretty slow. There must be a horizontal asymptote. Well, think about that. If there was some y value that this never went above, since it's the inverse of e to the x, that would mean on e to the x there's some x value that you're not allowed to plug into there. But we know that you can raise a number to any positive power you want. So that doesn't make any sense that there would be if there was a horizontal asymptote on natural log, that means there would be a vertical asymptote on e to the x, which there is not. But it grows very, very slow, which is an important thing to know. An interesting fact is if you were to draw this where each tick mark, 1, 2, 3, 4, was an inch on your picture, for this thing to grow to a height of 42 inches, so not even 4 feet, you'd have to go over this way to Alpha Centauri, so the next closest solar system to us. So it goes, which I think is like 1.6 times 10 to the 18th inches, or roughly 5 light years. So natural log goes up 42 inches over 4 or 5 light years. So it's very, very slow. But it does keep growing and growing without bound. So keep in mind, natural log does go to infinity. So we are looking at, then, a form here of infinity over infinity. And we can use L'Hopital's rule on that form. So derivative of natural log is 1 over x. Derivative of x is 1. And again, whenever you use L'Hopital's rule, I want you to state that that's what you're doing, so it's clear how you're getting from one step to the next. When you simplify that, that's just 1 over x. And as x goes to infinity, that goes to 0. Now, there's a couple of interesting results from what we just did here. First of all, one interpretation of what we did is that we compared the long-term growth rate of these two functions. Right? We put them in a ratio, and then we just went out to infinity. If they had roughly the same growth rate, they would fall into some nice ratio, and we'd get a number here like 4 or a half, something like that. If natural log grew much, much faster than x, this ratio would take off to infinity. If x grows much, much faster than natural log, you'd expect that to get smaller and smaller and go to 0, which is exactly what we got. Which makes sense, because as I just got done saying, natural log grows very, very slow, right? Think about that. The function y equal x, which is this, for it to go up 42 inches, all you have to do is go over 42 inches, right? Up 42 over 42. On natural log, to go up 42 inches, you have to go over 5 light years. So much, 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 much slower growth than this. And so it's not surprising that our result is that that limit is 0, because the bottom is just so much bigger than the top. It's getting much, much, much bigger. So one interpretation of this is a growth rate comparison. Our result here, that's telling us that x grows much faster than natural log because that limit is 0. A result of that is it tells us that even if it's not true at the beginning, although it is true at the beginning, but in general, a limit like this tells us that eventually the bottom function must end up being bigger than the top and stay bigger, right? Notice, what does this mean? If it's getting closer and closer and closer to 0, that means eventually natural log of x over x has to be less than 1, right? If you're getting infinitely close to 0, obviously at some point you're less than 1. And if I multiply both sides by x there, I get this inequality. This will be helpful for us later on. The fact that we can argue that natural log of x is less than x. And it turns out that we can say something even more general than that, but we'll get to that later. So you can use L'Hopital's rule on stuff of the form 0 over 0 or infinity over infinity. And it can be any combination of positive and negative infinity there. Now there's some other indeterminate forms that you can't directly use L'Hopital's rule on, but you can use a little algebra to manipulate first, and then you can apply L'Hopital's rule. So we'll look at some of those situations next.